Alrighty, good morning, Biology 20s. I just wanted to continue on. I started talking last video about enzymes and their structure, and we also talked about enzyme activity, so understanding that temperature is going to affect activity. Activity increases to a maximum and optimum level, and then as the temperature continues to increase, the enzyme begins to denature, it unfolds, and its active site can no longer bind to the substrate. We also know that pH is a very important factor in enzyme activity. And again, enzymes have their maximal, their best, their optimum pH that they work best at. Anything below that or above that, enzymes begin to denature, they unfold, and they undergo a shape or conformational change, and the enzyme and substrate can no longer bind. What happens when we increase the amount of substrate? Well, our reaction rate at first is linear, it increases, and we are able to have a higher reaction rate, but then you see on the graph that it starts to level out. At this point in time, the enzymes are full, they are reacting, and there's lots of substrate, but there's just not enough enzymes. And so the enzyme becomes the limiting factor, and that level reaches its maximum, it flattens out, it plateaus. So then we can also look at enzyme concentration. As we increase the amount of enzymes, there is more reaction rate. The reaction rate goes up in a linear fashion, but again, this level can plateau. If we have lots and lots of enzyme, but not enough substrate, then the substrate is the limiting factor, and the reaction rate levels out and it reaches a plateau, and that's that flat part there on the curve. Okay, so what about enzyme inhibitors? Well, unfortunately, there are things that stop an enzyme from acting, and so they inhibit or prevent enzyme action. Two major classes of inhibitor are competitive and non-competitive inhibitors. So a competitive inhibitor, as the word says, it competes. It is going to be in a competition, a fight for the active site. And so here is the normal substrate, and he would like to join with little Pac-Man, the little enzyme. There's his active site, but you can see that the competitive inhibitor has already beat him to it. And so it is preventing, it's blocking that substrate from being able to bind. The competitive inhibitor has a very similar shape that allows it to fit into the substrate. And so poor little substrate, oh, denied, can't get in. Okay, and so the competitive inhibitor prevents the substrate from binding to the enzyme. So what is a non-competitive inhibitor? Well, a little bit different. It is not competing for the active site. The non-competitive inhibitor typically binds to a site other than the active site, which is often like on the backside of the enzyme, and it's called the allosteric site. So what happens is once the inhibitor is bound, you see that there is a shape change here, a conformational change. And now the active site can no longer fit the substrate. So again, substrate tries to bind, can't fit anymore. Uh-oh, denied, can't get in there, right? And so no enzyme reaction. So both cases are going to lead to a decreased amount of enzyme reaction rate, right? Here is our normal enzyme, the normal reaction rate, and of course we know that the substrate concentration increases, but the amount of enzyme will limit that. Competitive inhibitor is going to increase the rate at which that increases, right? Because there's more competitive inhibitor. You can still get reactions, right? Every once in a while that substrate is going to beat out the competitive inhibitor, and he's going to get in there and bind. And so we can still have reactions, but that's a different case when we have this non-competitive inhibitor. You can see how much the reaction rate drops because that non-competitive inhibitor is making that enzyme so that his active shape is changed, and so he is no longer able to bind. So here's where the inhibitor binds, active site changes shape, and he can no longer bind at all, right? And so that's why the reaction rate decreases. Okay, one more thing that we need to know about before we finish up on enzymes here is feedback inhibition. So a lot of times, like for instance, cell respiration, when we start with looking at glycolysis, we have a whole bunch of different enzymes that are involved in breaking down glucose into pyruvic acid. So there's a whole bunch of enzymes and a bunch of intermediates that they create. So here, if we have our substrate, and that is glucose, and enzyme number one, it makes an intermediate product, and then enzyme number two makes another, and we keep on going until we get our final product. So we have this pathway, and you guys know that the final product is pyruvic acid or pyruvate. And you know that there's a whole bunch of different steps. We didn't have to memorize them in Bio 20, although if you ever go to university, you have to learn all the steps and all the chemicals and all the enzyme names. But the point is this. The point is that there's this process called feedback inhibition. Once this product starts to build up, it feeds back. It goes back to that original, that first enzyme, and it blocks it and says, okay, that's it. You're done. You're not acting anymore. So no intermediate is made. No second enzyme gets to act and make that intermediate. This whole process is blocked from there on out. So that is inhibition. It stops the product from accumulating or building up in the cell. And it just simply means that you can't have too much of a product build up. And so this is what we call feedback inhibition. It's one of the ways your body has to regulate the amount of enzyme activity. Okay, so that is it for enzymes, factors that affect enzymes. You guys have some practice questions to work on. And until next time, you can get a hold of me, michelle.ladine at ghsd75.ca. Talk to you later.